We may now start introducing each other and get started with the session.
Uh, Hello, I'm hoster Yapen Mi, and the first speaker is Brock Starter, and his speaker is seeing the culture, and now let he share paper with us, right?
Yeah, okay, let me share my screen. Thanks, Yapen. Okay, I think you can see my screen, right? Okay, I think all's good. Yeah, let me start.
Yes.
Okay, so, okay, hi everyone, and yeah, thanks for the opportunity of Sungjun, and yeah, thanks Yapen for the introduction. So I will present our recent work, which has been accepted for the EMNLP conference this year. Our paper explores visual reasoning and grounding within a cultural context, and we have three main contributions. We create an image dataset for cultural artifacts in Southeast Asian cultures, which is underrepresented and diverse. And the images are complex with many distractors, and each one has reasoning question generated by cultural experts, which I'll explain, I'll share. And we design novel benchmark via two-stage approach. We first evaluate VLMs in multiple choice questions. And if it chooses the correct answer, then we evaluate how well it can visually ground this cultural artifact to prove its reasoning. And lastly, our experiments highlight the drastic gap between visual reasoning and grounding of VLMs on especially cultural artifacts. So I'm a research scientist at SMU under the guidance of Prof. Chonwa, and this project was made possible thanks to the co-authors from Singapore Management University as well as Bandung Institute of Technology in Indonesia. So if you start from background, multimodal visual language models have made substantial progress in various tasks that require a combined understanding of visual and textual content, especially in cultural understanding tasks, thanks to the emergence of new cultural datasets. However, they address cultural understanding rather than reasoning. And which we can also say even visual grounding task, there's one paper from last year, EMNLP. It also addressed cultural understanding, which I'll explain, but let's say this is Molinolo. It's a traditional thing, if I remember, Mexican, if I remember right. So we just want to detect this by just naming it. So to make our point clear, let us dive into the difference between these two, cultural understanding and reasoning. In understanding, the questions directly refer to the cultural artifact, which is here. However, we want to know whether VLM can reason over the symbols without explicitly mentioning the cultural artifact. Yeah, for example, in the left one, Rafflesia is one of the Indonesia's three national flowers. But here in the right side, we are talking about some symbolic meaning of some cultural artifact, we can say. So tasks actually, but there are few tasks still recently on cultural reasoning. And some of them we can see that very limited, and although their aim is not that specific. So the issue with the recent cultural reasoning benchmarks is that their tasks are not challenging, and would getting the correct answer be enough for us to believe that VLM can reason in a cultural context, which is not true. The question is, can we really trust this visual question set up for reasoning? Which in a way they're addressing this reasoning, but to very limited extent. And what I mean is, for example, for instance, this work shows that there could be some spurious correlation between questions and textual options. And if the VQS setup is like something like this, as we see, textual question, and there's one image and the options are textual. And long story short, there could be some spurious correlation between questions and options. In a nutshell, this work suggests that VLMs can answer this question without looking at the image with the high probability. So how can we overcome this potential risk in a new benchmark? That was one of our motivation. Another one, some paper uses this multiple choice visual question answering and ask VLMs to explain their choice of options to prove their reasoning, which then uses VLM judges to this answer. So basically, we also argue that this could also bring some bias from VLMs, although can be useful in some cases, but it's also open to biases that can come from VLMs. But also, this work also shows that this another recent work shows that even judges can be deceptive, which could derail the VLMs. So we argue that VLMs cannot be that trustful in the cultural context as a judge. Another one, cultural reasoning datasets are limited. So one elegant way would be using visual options in the question rather than textual options, which this paper does it. But however, these are very simplified version pictures, which it's hard to find in the real world, real image data or real world videos. Highly filtered images, which only you see what you see is only cultural artifact, no distractor, and nothing else. So would VLM grant this cultural artifact within a complex image? We don't know. We want to see this as well. Whether this can be useful in real life or not. And lastly, I can say that current benchmarks do not primarily focus on underrepresented cultures, mostly Western or some recent one Chinese. And the questions are mainly generated by AI, and humans are only used in the refining the last part or eliminating some questions. So using this kind of formula in AI may not reflect natural questions that can come from real human interaction. And segmentation masks are generally bounding boxes, which these cultural artifacts are you'll see now very quite small, and these bounding boxes may cause losing some fine-grained details of cultural artifacts. So after all, to address these all shortcomings, we introduce Scene Culture Benchmark. It contains over 1,000 images, capturing over 130 cultural artifacts across 5 cultural themes: wedding, game, music, celebration, and dance. And the countries: Indonesia, Malaysia, Cambodia, Vietnam, Thailand, Philippines, and Myanmar. So here are some of the pictures. Let's say this Shamprok dance from Myanmar, and this shuttlecock kicking. And yes, we segment all of these cultural artifacts, and as you see, some of them as multi characters or multi artifacts. Like here in this dance, Balinese leg dance, there are 2 characters. You may see. Yeah. So. Yeah, these are some statistics about our data set. So one of the limitations, which as you may see here, yes, there's still a bit fine grain, although we did our best. For example, Cambodia, it was not easy to get images. I mean, even if you get images, it's not easy to get cultural experts to annotate this data with the reasoning question. So, but still, it was a nice attempt. And yeah, in ongoing work, we are doing our best to address this. So if I look at the task, deep dive into the task, so there are 2 parts, which is in the first part, there's a reasoning question and only 4 visual images, and we ask about these cultural artifacts. And if it selects the correct one, we ask VLM to, okay, then can you please segment this by asking the same reasoning question. Only difference between these two questions, we just convert this into from MCQ way to segmentation way, actually. Some small transition. That's the only one of the parts that we use AI to convert the question. And so there are three types of questions. Let's say type 1, all these options are coming from the same countries. Let's say this cultural artifact is about Indonesia, which the true answer is D. And A, B, C are from Indonesia, let's say. These are some lion dance options. And type 2 means that all of the options are coming from different cultures. But again, yeah, I forgot to mention the options are from the same category, which is in this case dance, but only what it changes country. And type 3 is a fair mix of type 1 and type 2, just two of them different and two of them same. It's kind of a balance between. And we use some quota to choose by following an algorithm. There's a quota to use some certain amount of artifacts to prevent some bias in the questions, in the options. So experiment shows that type 1 is about 25% more challenging than type 2, which is also logical if the options are, well, let's say questions, let's imagine questions are same. If the options are from the same country, it's more challenging for VLMs to find the true answer. And the other one, we see that open source models in stage 1, we can see that the closed source models outperform open source models in stage 1. And we can see this result over the category and countries. Okay, let me check my time. So to go a bit faster, so we can see one of the example here. Let's say I'm giving this example just to show that, just to give you another example of complexity of data. For example, this part, we are asking, there's this granola, this kind of small guitar here coming from Portuguese culture back in old days, but these are normal guitars. So we are also asking about these to segment VLM. To be a bit more quick, in the second stage 2, let's consider stage 1 is passed, and we see that generally Q1 is better, having a better result, which is open source are better here. Yeah, I mean the outcome is in the stage 1, closed source models are better. In the stage 2, open source models are better. Yeah, some other extra details. We see the similar trend in the category-wise and country-wise, actually. For example, we can see some failure cases here and here that, let's say let's look at the stage 2 one. I think only GPT answers this correctly in stage 1, GPT-03, but in stage 2, none of them can. And this is the outcome of, I think, Q1, which is the answer should be this left guy, but it selects the rightmost. And these are different characters in this dance. So conclusion, can say that seeing culture benchmark focus on cross-model visual reasoning in diverse and low-resource cultures, specifically in Southeast Asia. And we introduced this two-stage evaluation, combining visual question answering and grounding for cultural reasoning. And the outcome is we highlight the disparity between visual reasoning and spatial grounding. So basically, we ask VLM, okay, find the right answer. It finds, but okay, give me the reason, give me the proof via segmentation. no, cannot, even though normally can in other objects, in normal everyday objects can reach around 80% accuracy in some recent works, but in our dataset cannot pass over 40%, 30%. And yeah, I already said this. Yeah, these are some small outcomes, but for the last 1 minute, maybe I can give quite future work. How about we use RAG to improve segmentation results? We are now a bit working on. And how about spatial temporal reasoning in video domain? That also would bring some other extra things that we are working on. And these are some concepts that we are using. And as you see here, Cambodia, we have very less, but Myanmar, we have more. Philippines, okay, and etc. And just to say that we eliminated this kind of, for example, images, just to make the data set more realistic. And yeah, I can talk later if any question about future work. If not, I can end it here. Considering it's 50 minutes.
Thank you for your presentation. And I have 2 questions. The first is the data set I see is collected in some source Asia, and it is easy to transfer to the world, a culture knowledge, or just beyond the Asia.
Oh, okay, that's a great question. If I answer in a two-way, yeah, that's the exact reason we choose data set a bit realistic, so that we can a bit quickly implement this in maybe real-world application if possible. For one of our main motivation to address seeing that there are data sets in Western culture or Chinese culture, but not in Southeast Asian culture, which was underrepresented. That was our first aim to have this benchmark. But yeah, definitely this kind of thing can be applied in other cultures. But honestly, yes, it's not that easy to scale. We use less AI here, although it give us sorry, high quality data set. However, it's not easy to scale. Definitely, there should be a way. We are still against using pure AI, to be honest, but there should be a nice, clever way to using this AI and cultural experts to come up with questions and everything. So we have actually even more images in our data set, but we couldn't find a nice, high quality experts to annotate. So I mean, getting data set one thing, but also having a high quality annotation is another thing. If we can solve this kind of things, which we are actually working on, yeah, definitely this can be applied to another cultures, especially in other underrepresented cultures. Yeah, thanks for the question.
Okay, thank you. And the first is I see some culture is in different languages, and the correctness or the quality is infected by different languages, or because the one VLM is not equal in different kinds of languages. So I think this is this influential?
Yeah, that's a very nice question. I like the question. Honestly, we didn't do nice analysis on this, but before we applied any, I mean, we check all of the VLMs that we use. That all of them are familiar with these languages, and in our questions, we try to use the local version of it. Let's say we didn't say shuttlecock kicking. Instead, we said da chao. If I say correct, which that must be, or Thailand, we use this in the question. We didn't do this analysis in our recent work, actually, which now we're working on video, similar work, but in video domain. yes, we realized this can be one of the effects. And thanks for reminding this. Yeah, we are hopefully working on this now. That it would be nice to have one questions with just maybe only international or maybe only English version of concept, which is this Legong dance or maybe other thing, Tacha. But in one version only the local version, local transition of this concept. That would be nice to see. Yeah. So long story short, yeah, we don't have, but that's a nice to have. And thanks for reminding me.
Okay, thank you. And I have no questions.
Okay, I'm stopping then.
I have some extra questions. So,
Sure.
perhaps not particularly about this work itself, but I wish to understand your viewpoint on the ideal models, right? So, do you imagine a model which is knowledgeable about all cultures around the world, or do you think maybe it's okay for a model to focus on a single culture at a time, or even have this knowledge as kind of an external source, not necessarily inside its parameters, but it can do sort of Google search and get the results and include that in the answers? What's your vision on this?
Yeah, let me share my screen on this again. That's a nice question. Many things to say. I say maybe I start from the last one. Yeah, we are now working on the we did some analysis actually, of course. We although not that much I mean we are still lacking some analysis, but this is one of the analysis we did. That we realized that actually the VLM, some of the VLMs they don't know about the or some of the VLMs yeah, when we ask the um, things that they actually answer in MCQ, but in stage in the segmentation part, the reasoning or the idea is completely not complete, but not that correct. And maybe yes, giving the correct cultural knowledge, let's say via reg or Google search, would increase the segmentation. In a way, we see this in a bit. This is still ongoing work we are working on. So that would be one of the thing we are working on again to increase the segmentation part. Yeah, for example here. Oh yeah, I didn't share this to you. Yeah, same. We we know that this VLMs or even segmentation models we are also checking. They know the culture, but still, sorry, they don't know the culture, and that's why they lack some cultural knowledge, and that's why it affects the result. That's one thing. But also about the first part you said. Okay, I think this culture thing is important in a way that, uh, of course, I am not sure, but that's what I see. So, for example, in few years we want to see some personal assistants on maybe in a new device or phone or anything, or using somehow AI. But let's see if this AI doesn't know about your culture very nicely, very clearly, how can you trust this AI? Or from the perspective of companies, how can these companies sell this to the people? Probably that's one of the things to connect this AI to the humans. This cultural match, I think, very important. And yeah, just showing some of the reflections or um, some of the parts of this gap actually. And probably once this is solved, there could be higher this AI human match or AI human interaction would be softer and faster, I believe. For that, definitely, yeah, I'm not sure on this, but one dominant, one big culture that knows everything probably may not solve. That's why we do our best to represent underrepresented cultures. And probably in the company view, that would be also an advantage to reach more people, probably. But yeah, it's a deep philosophical question that we are also thinking.
Mhm.
Yeah.
I think thanks for the answer. And by the way, thanks for the great presentation in the first place. A follow-up question would be, I'm identifying like two different ways to solve this benchmark. One is
Mhm.
just relying on some external knowledge and just making sure that everything, every answer is correct from this model, right? I don't care if the model has this knowledge
Mhm.
internally or not. I just want the model to kind of connect to the relevant information somewhere, and I'm good. But you also seem to suggest that there may be some kind of downstream value for a model to contain this cultural information, maybe perhaps beyond the benchmark itself, where the model now has better understanding of the culture and therefore it can also do something else, right? Kind of, for example, increasing the trustworthiness of the model for the other part of the question, not necessarily cultural questions. Or I don't know. I'm also coming from a stronger kind of cultural background, which is less
Oh,
represented in those models. So I wish to have a model which is kind of understanding the way of thinking for my type of people. And you
yes,
know, yeah,
definitely yes.
so if that's really what's needed, then I want this information not to be just present in these answers to multiple choice questions, but
True.
I want to make sure this is used in the thinking process, for example.
Exactly right. That's the one of the important thing that also push us recently. For example, I didn't share here that we have another video actually, but that's why we are actually also working on video, which that's why because we want to use in the end of the day, if possible, that would be great if we can use this in a product maybe, um, or at least real life videos. That would be great to know that I'm asking this kind of thing and want to know where does this happening. Yeah, rather than just MCQ. I had one good example for this, but yes, never mind. This is still okay example that would bring even more real thing, even temporal reasoning and temporal um, cultural understanding in this temporal with this temporal reasoning. Um, yeah, um, but yeah, thanks for the last part that you just said. Yeah, I
Yeah,
fully
thanks a
agree.
lot.
Okay, then. So that means we continue the next one. Okay. So next talk will be done by Yapeng Mi, and uh, it's about uh, MILR, improving multimodal image generation via test time latent reasoning. Yeah, Yapeng, uh, you may
Okay,
start anytime.
thank you. Can you see my PowerPoint?
Yes.
Yeah, okay. I am the speaker, Yapen Bi, and I come from University of Science and Technology of China, and I will introduce my paper MILR, improving multimodal image generation with the test time latent reasoning. And here, I want to first talk about text-guided image generation. There are two main kinds of paradigms that can do image generation. And the first is diffusion. The famous example is Stable Diffusion 3 and Flex Render. And the diffusion first makes data, and when training makes data into the noise, and when inference, and it diffuses noise to our generated image. And the second paradigm is autoregressive. This is inspired by text generation by next token prediction, and naive autoregressive image generation is next image generation prediction. And the other is VAR and next scale prediction. As an example is Llama EMU3 and Show Genius Pro. And this paradigm makes it feasible to build unifying the multimodal understanding and generation models, which is famous in recent studies. And we find image generation needs some reasoning ability. And look at this case, and the prompt is the flower that symbolics purity in China, and answer is lotus. And the only prompt, we only put prompt into the ST3 medium, and it will output one pink flower that is not the true answer. But we input it with answer, just the lotus in prompt, and it will output the right picture. So the model knows what is the lotus, but the model doesn't know what is a flower that's symbolic purity in China. So traditional models are limited in generating image in a single shot fashion, thus unable to resolve potential defects. So we think image generation needs some chain of thought prompting, just like you can think and know the right answer and generate. Inspired by the success of reasoning augment LLMs, such as O1, DeepSeek R1, and recent works have endured reasoning ability into image generation. And when talk about reasoning augment image generation, there are three ways. The first is reasoning in a language space, just like Reflect-IT, and it uses a feedback VLM to judge the generated image if it satisfies the prompt, and if not, it will modify the prompt and put into the DIT to generate twice. This is reasoning in the prompt, just a text language space. And the second is image space, such as PLM, and it use show, and it use a judger to judge the intermediate image tokens, just let the right tokens to continue to generation, and let the bad stop the generation, just like showing the image. And the second is reasoning in language and image generation, just like G2IR1. It uses the GRPO training method to train unified LLM and make it first to generate explanation prompt that explain the image prompt, and then use the schematic COT and image prompt to generate the final image, and just use GRPO to train it. And it performs reasoning in language and image spaces. However, early works, just like Reflect-IT and PARM, lack a mechanism for simulating reasoning across two spaces, and the T2IR1 just require carefully curated reasoning data and depend on model fine-tuning. It is complex and costly. So we want to make a method, MILR, just multimodal image generation with a test time latent reasoning. We want to make it perform in test time, and we just bring latent reasoning into this. And this picture illustrates our one teaser, and you just impose a photo of three kinds and unified MUG model outputs the text and the images. And we can say you can use this ZT and ZV and do some latent reasoning. This stands for latent reasoning, and then it's regeneration, and then it's regeneration until it satisfies the three kinds. So our method reasoning a unified latent vector space that encodes both text and images. Just it is a character of MUG model. And then second, it uses policy gradient method to perform test and image generation without fine-tuning. It just performs in test time, making it somewhat efficient. So this is our main framework. You can say in this picture, and in the instruction, this is a case, a photo of the birds. We input the unified multimodal generation model, and we extract the outputs of the last transformer layer. It will output just a vector. This vector can encode text latent space and the image latent space. So we call it unified latent space. And we optimize this latent space. Our core policy for optimization is as follows. It is a reference algorithm because it is very simple and it is easy to use. So we use this algorithm to optimize this latent space, and when for one term we decode it into text and we decode it into image. It is all regressive manner, and we just decoded the image tokens into image to let it the reward model to judge it, and it will give a reward just like 0 or 1, and this will guide our method to optimize points. If it satisfies our instruction, it will just output, and if it is not satisfied, and it will just re-input and optimize it. So this is our main mechanism that we can do test time latent reasoning. And our experimental explanation, and I put my algorithm MIL and our latent reasoning method into it, and our just algorithm needs a very simple algorithm, and our core algorithm is this latent reasoning, and then we have 3 kinds of latent reasoning. First is joint. The second is ALT, and the third is P2A. Joint and means we can optimize the text latent space and the image latent space simultaneously, and the ALT will I will just optimize text first, image second, text first, image second, and this interleaved manner. And the T2 we just means we optimize the text and then the video. So it is 3 kinds, but in our experiment we just use the first by default. And our base model, we choose Genius Pro. Genius Pro is a strong model that supports unified understanding and generation. And for generation and understanding, it uses a single transformer to output the language and the image. So it provides us with a unified latent space. So it is suitable for our method, and our we can see our only optimize a subset of the token of the latent space. So we set friction set lambda t equals 0.2 and lambda v equals 0.02. So we use a DAM optimizer, and we set the learning rates equals to 0.03. And we just use a single NVIDIA A180 GPU, and it is efficient because we do not need training. And let us to see our main results. We just test our method with Genius Pro in 3 benchmarks. First is GenEvo, and second is T2I EcoBench and Voice. And for GenEvo, we just achieve good performance. And for our T2I EcoBench and Voice, we achieve just surprising performance too. And this two tables in both our method achieve good performance across general T2 bench and voice benchmark. And the second MLI hypothesis foreign tier non-reasoning models, we just list three kinds. Non-reasoning models means just one single shot model, just like SD3 media and Bagel, and the training-based reasoning models, just like GOT-R1 and T2I-R1, and just variants and the test time reasoning models, just like reflection flow and PLM. So it shows that when optimizing the latent space, it is efficient and useful in just different kinds of benchmarks. And then we also do some qualitative results. And as we can say, MRL is capable of dynamic temperature and culture reasoning, just like as seen in this picture. And one example I want to share is just like this: the Great Wall of China when it's 3 p.m. in Los Angeles, and the ground truth is 3 a.m. in China, and ours well outputs outputs the right answer and right picture and the Genius Pro and the T2I-R1 and then the Bagel, or outputs the wrong answer. It just like the afternoon in Great Wall. And this case is Lotus, and Lotus we just our method outputs the right answer. And the following is a detailed case of our method. And when we input a prompt, and it will just output text just like this, and the image and our the yellow and the picture is optimized to hit token hidden states, and it will just do latent reasoning and into the next decoded text and the next decoded image tokens, and just like this. And you can say in the first it generated wrong text, and the second it just point out it should generate right lotus flower with a yellow center and a few green leaves and water tails. So just by just this optimizing, it will generate right text guided and the right image. And we also do some ablations, and the table 3 is ablations of our MIR on GenEvo, T2I Cobench, and voice. And we can say joint image text reasoning in unified latent space leads to the best performance, just like the first line. And when we without this MIR, it drops at the lowest performance. And without image, it will choice for just the second best, and without the text, it will drop the first. So when we without text, it is more worse in than without image. And the following is our qualitative cases study. And you can say our original is really bad, and our both it will lead to some good visual and text and image. It is not good than both, but it is better than the orange. So we also do some analysis. Just we can say our optimization is a test time method, so it can be scaled but with the optimization steps. So we just test the performance across 3 benchmarks for varying optimization steps. And as we say in general, T2I Bench and voice, it's just improve with the increased steps. Just but however, it for some benchmarks, just like general, it will reach a top and just stayed in it. And the T2I bench and voice same T2I bench did not have this observation. So we just say scaling up the number of optimization steps improves the performance on all benchmarks. And we also analyze the text token ratio analysis and the image token ratio analysis because we just optimize the prefix subset of token hidden states in our paper. So and we say we just start from 0.1 to 1, and we can say optimizing a moderate amount, just like 20%, just like in text token ratio, and will lead to the best performance. So in our experiment, we set the text token friction into 0.2, and we just say in image token ratio analysis, optimizing a tiny amount, just 2% of image tokens gives rise to the best results. And it is very interesting that if we increase the image token, just a very, very small friction, 0.01 and to 0.1, it drops fast. So it is more faster than text. And so we think our autoregressive image generation is highly influenced by the first token. And we just also do some reward model. Just a reward model analysis. And in real world scenarios, Oracle rewards are usually unknown to show that MRLR is efficient without reliance on an Oracle reward. Because in the following results, we use Oracle rewards to do it. We test it with a set of off-the-shelf reward models, just in Jable, into T2IQ bench. And we say using other rewards models also leads to improvements than the baseline, just like in Jable, the overall from 0.78 to 0.87. And in T2IQ bench also have this performance. And we just illustrate the bar chart that shows the performance obviously, and you can say the Oracle reward is the best, and the we use the this mixed reward. We just combine different kinds of reward models, and our unified reward model follows with mixed reward and GPT 4.0 and is just comparable with unified reward, and the self-reward is lowest. So it shows that MLILR is reversed to different reward models. And then we also analyze our error cases. There are three kinds of errors that in our optimization. The first is textual reasoning collaborations. Just you can say it will optimizing and it leads to repeated text. It influence the final generated image. And the second is visual reasoning collaborations. And we can say just the first line out in red, and it is it drops and it reversed. So we think it is leads to some kind of wrong generation. And second is reward hierarchy. Just like a reward model, if we say a photo of bench above a spawn, and you can say this span in 3D world it is not above the spawn, but in 2D world the reward model thinks I think it is above this point. So it is wrong, but it is a kind of reward hierarchy. So maybe adding a regularizer like semantic incoherence helps, but we think it is a future research and it will be resolved in our future work. And when talk about future research, we just think there are three main directions. The first is generalizable. It is interesting to say if the effectiveness of MRLR transfers to different based MUJ, just like show and others. And we think design better reward models is better. Our experimental results show have relieved that the strongest non-Oracle reward model still lags behind the Oracle reward. Thus, future work is well suited for designing reward models that can generalize in different domains. And the third is another paradigm. Maybe it is interesting to see another paradigm of latent reasoning image generation. Just we do need in test time and maybe training and maybe others. So that's all. Thank you for your listening.
Yeah, thanks, Diapeng, for the great presentation. So I can quickly ask, so what's the test time, compute, and latency overhead of this policy gradient reasoning? I mean, compared with the standard mark inference, maybe? Or
So
do
you
you
want
have
to
any,
ask latency?
do you have an analysis of this policy that you came up?
We
Yeah.
analysis it into the paper, and I do not
Ah,
put it into this PowerPoint. And the latency we just test it. For example, you do best when and you do best when is run on the just we say it is run
okay.
on the this Gen Evo benchmark, and best when if we set n equals to 20, and it can cost 8 hours, and hour cost 5 hours. So it is slower than 3 hours. And we compare it with test time reasoning models. Just we have a better latency because as you can see, our method will early stop. If it satisfies the reward model, it will output, and it will not just optimize. So it save time. And when compared with just training-based reasoning models, or we do not need training, so we save the training time. And but when inference, the training-based models are faster and ours are slower. It is obviously, and the non-reasoning models is also. So I think our method, the latency is in a reasonable level.
Yeah. And also, can you go back to the error page? So when you look at the errors, is it generally because generator constraints or anything else? So when you look at the error cases, or yeah, what's the main or second main reason for this causing this error?
Just you ask benchmarks or model?
Yeah, there are some error samples that you in the latest page. Can you go back? That's like error, the failure cases, failure cases. Yeah, sorry.
Yeah, failure cases is showing these error cases.
Yeah, yeah. So what's the main reason you think is because of some constraints in the generator, or some limits to or some other
I
things?
think it's because you optimize the prefix tokens, and the prefix token in autoregressive manner, the prefix token will decide the later tokens. So if we optimize it into just our unknown vector, it will lead to some unknown outputs. We cannot predict, and it will. But however, it will uh, it will occur. So we just optimize a small set of prefix tokens, not all tokens. We test with all tokens in the paper, and the whole image, the whole text, and the whole image will become not readable. And we test it in it. And these three kinds of error cases, the former is due to this reason, and the second the third error is due to reward hacking, just like error one and error two is the one problem, and the error three is the other problem. So
yeah, they're very nice insights. Having this error, having these insights, it would definitely lead nice future work. Yeah, thank you.
yeah, okay.
Thank you. I also have one more question. So I wonder, thanks for the great presentation, by the way. It's really interesting how the latent reasoning works in diffusion models. I wonder how the reasoning is helping. So, do you have an analysis, for example, of cases where reasoning has boosted up uh, the the performance a lot, for example? Or did you also look into the mechanism by which the reasoning is improving some of the cases?
Yeah, I just
Yeah.
know your question, and the reasoning helps because we first think reasoning image generation needs reasoning, and we show some quality results. The former is just a comparison with other models. The following is our whole image generation, and we just marked the wrong text and our image in red, and you can say if we just generate the flowers that symbolize purity in China. It is lotus, and but the first text says it have five petals. It's pure white and blossom surrounded a soft green core. It is not right because it did not point out the lotus. However, when we optimize the prefix token hidden states and its regeneration, it says it depletes a single white lotus flower. So the answer is generated, and the yellow center and just marked green, just a few green leaves and water lines, and it uses text, and we also simultaneously optimize the prefixed image token hidden state, and it regenerates the right answer. And this is, I think, it is a kind of phenomenon that reasoning can help generation in our method. And the second case, a photo of three sports balls, and you can say it generates wrong text with one ball in the foreground and two in the background. It just have misread just a semantic. But however, we regenerate it just like one ball in the center and the other two on other sides. As the central ball is red, white, and other two balls are blue and green. It is a very semantic influence, and it generates the right images. So we think this is a kind of evidence that reasoning can help image generation.
Thanks a lot. That answers my question quite well. Okay, so thank you, both of the speakers today for the great presentation and great discussion afterwards. Again, this is recorded and will be put on YouTube. Let me know later on if you want anything else. So thank again the speakers,
Yeah,
and
thank
let's
you
keep
very
in
much.
Thank you, Simon. Thank you
Thank
very
you.
much.
Let's keep in touch on Slack if you wish.
Sure.
Good. And we'll soon move on to the next session on
Okay, thank you.
diffusion models. Feel free to stay if you wish.